Hi all, my name is Daniel Valcarce from the University of Coruña, and I would like to talk to you about our work on studying the robustness and discriminative power of different evaluation metrics for top-end recommendation. So when we approach evaluation in recommender systems, we can distinguish two main approaches. We can perform online experiments, which involve users in the loop. But in these kind of experiments are usually expensive, but they really measure the real user behavior. In contrast, offline experiments are very cheap to and very highly reproducible. So they usually constitute the first step in the development of recommender systems. So this work focuses on this last part, this type of evaluation when we have a dataset and we want to perform experiments in offline fashion. So one of the questions that we have to answer when we have an offline experiment is which metric or which set of metrics should we use. There are so many types of metrics. We have error metrics, ranking accuracy metrics, diversity, novelty, serendipity metrics. From the shift from rating prediction to top-end recommendation, error-based metrics has been demoted, and nowadays ranking accuracy metrics are really popular. But these metrics were also actively used in information retrieval in the past. For example, all of these metrics, precision, recall, MIP, NDCG, MRR, BPREF of InfAP, have been proposed and have been extensively used in information retrieval, but they are nowadays also used in recommender systems. But the thing is that information retrieval and recommendation are different tasks, although they are related. So we want to perform some evaluation on the metrics that has been performed in IR in the field of recommender systems. And in particular, we want to study these metrics from two different perspectives. We want to study the robustness of these metrics to the incompleteness of information, and we also want to study the discriminative power of these metrics. So how do we do that? Okay, regarding robustness to incompleteness, when we talk about incompleteness in recommender systems, we have two main sources of incompleteness. We have a sparsity bias that is just intrinsic to the recommendation task. We don't know everything about your users, otherwise there is nothing to recommend. So we only have partial information about our users, and we need to recommend relevant items. But we also have a popularity bias in recommendation, because information is not missing at random. Instead, information follows a long tail distribution where some items have a lot of information and we don't have a lot of information about some other items. So the idea is to able to control these kind of biases in our offline experiments in order to study how robust are the ranking accuracy metrics with respect to these biases. So for example, to control the amount of sparsity bias in a dataset, what we can do is to take random subsamples of the dataset. Regarding the popularity bias, we can control this bias by just removing the most popular items on the dataset. So the idea is to take the original dataset, take a bunch of different recommender systems, and evaluate them using different metrics. So each metric will provide us a ranking of systems. And now the idea is to change the amount of the sparsity or the popularity bias and evaluate again the recommender systems. Then we will obtain a different ranking, and we can compare the ranking with the original dataset and the ranking obtained with the modified dataset. And we can compute the kernel correlation of both rankings. And robustness was one of the properties that we want to study. The other property is the discriminative power of metrics. When we say that a metric is discriminative, what we are really saying is that what we really want is that the difference in its value is statistically significant according to some test. In particular, what we have used here is the permutation test with difference in means as test statistic. And the idea is to take this bunch of recommender systems and run this statistical test between all possible system pairs. And then we take the p-values of this statistical test and we sort them by decreasing order. So if we obtain a graph like the green curve, then we can say that this metric is highly discriminative because most of the p-values are really small. In contrast, if we obtain a graph like the right one, we can say that this metric is not very discriminative because the difference in its values does not indicate a significant difference. Okay, so now I'm gonna show you some of the experiments. I don't have time to go over all of them, but I will give you just an overview of them. Don't hesitate to come to the poster session to ask for more details. Our idea was to use different datasets. We use Moveland's library thing and Beaver Advocate datasets. And we follow the all-item methodology, which consists in ranking all the items in the dataset that has not been rated by the target user as candidate items for recommendation. We also performed an 80-20 random split of the datasets, and we implemented 21 different recommendation algorithms. So the first thing that we want to measure was how the cutoff of a ranking metric affects the robustness and the discriminative power of that metric. So first of all, we computed for each metric. Here I'm only showing the results for NDCG. We computed all the correlation values between system rankings when we rank the systems using different cutoffs of this metric. We can see that most cutoffs are really highly correlated with each other. So since all the with all the information, the systems rankings does not really differ when we use a small cutoff or a deep cutoff. We wanted to study how the robustness to the sparsity bias behaves. And we can see that in this graph that when we remove more and more ratings from the dataset, we see that higher cutoffs offer higher robustness to the sparsity bias. When we do the same regarding the popularity bias, we see again the same trend. Deeper cutoffs offer more robustness to popularity bias. And we can also see the same trend regarding discriminative power. A higher cutoff provides more discriminative measures than shallow cutoffs. So taking this result, then we compare different metrics with the same cutoff. In particular, we use a cutoff at 100, and we compare different metrics. Now we can see that some metrics are highly correlated, whereas other metrics are quite different, especially mean reciprocal rank is quite different from the rest of metrics. So again, we repeated our experiment regarding the sparsity bias, and we can see that precision and DCG are very robust to this sparsity bias. And in contrast, metrics such as MIP or mean reciprocal rank show poor performance with regard to the sparsity bias. When we do the same experiment with the popularity bias, we see again that precision is a very robust metric, and means reciprocal rank is again the worst, the less robust metric. Finally, regarding discriminative power, we can see that NDCG and closely followed by precision are the most discriminative metrics. And again, mean reciprocal rank provides low discriminative results. So what are the main takeaways that we can obtain from these experiments? Well, the first takeaway is that deeper cutoffs provides greater robustness to incompleteness and greater discriminative power than shallow cutoffs. We are not saying that, and when we use recommender systems, we usually only care about the top results of the recommendations. And when we are here recommending the use of higher cutoffs, we are saying that when we evaluate recommender systems in an online fashion, it is more reliable to use higher cutoffs, even though we only care about the top recommendations, because the results will be more robust and more discriminative. Regarding different types of evaluation metrics, we can say that precision is the metric that offers the highest robustness to both sparsity and popularity biases, and it also offers a quite good discriminative power. In addition, NDCG also provides very good discriminative power and high robustness to sparsity bias, but only a moderate robustness to the popularity bias. So in case that we are performing offline experiments, these two metrics should be preferred. And as future work, we want to expand this work on different types of metrics, for example, novelty and diversity metrics. And we also want to explore different offline evaluation methodologies instead of all items, such as 1+ random. And in this experiment, we also use a random split for training and test subsets. So in the future, we also want to study if other splits, such as the temporal split, will affect these results. Thank you for your time, and we'll be happy to take any questions.
Do we have any question? So, can you elaborate a bit more on the future work that you mentioned, particularly in this diversity and novelty metrics? How would be that process for evaluation?
Yeah, there are a bunch of diversity and novelty metrics out there that mean like how unpopular are the results, so they measure how often are different portions of the catalog being recommended. So the idea is to follow the same approach that as we use for the ranking accuracy metrics. We compute these metrics for the whole data set, and then we alter the biases of the data set, and we measure the robustness. Regarding the discriminative power, it could be more difficult for some metrics that are global, so we cannot do a pair test. But there are also some metrics that can be computed for each user independently, so we can also follow the same discriminative experiment.
Okay. We have some questions there?
Yeah.
Yeah, hi. Thank you very much for a nice talk. Chris Stratner here. So I was just wondering how you were computing your correlations, with the candle tau. Was it on user level, or how did you do this?
Yeah. So the idea is that we take the whole data set, and we, with this data set, we run our 21 recommendation algorithms, and we evaluate the results of these recommender systems with respect to some specific metric. This metric will provide us a ranking of systems. So then we modify the bias, or the sparsity or popularity bias of the data set, and we run again these 21 recommendation algorithms with this modified data set. And then we evaluate the results of those recommendations with the same metric. And then we have a different ranking of systems. So the idea is to compute the Kendall correlation of both rankings to see how similar or dissimilar they are.
Okay. Thank you.
Welcome.
Yeah, we have time for one more question.
Okay. Thank you, Marijn Kolen. Do you have any suggestions on how to deal with those less stable metrics for a situation where, for instance, you only show 5 recommendations? So I know I get more stable evaluation deeper in the list, but the user never sees it. So what do I do with that?
Yeah. And that's a very good point. Because if we are only showing 5 recommendations, it seems like not very intuitive to evaluate like 100 recommendations. But the results show that evaluating with a small cutoff or a high cutoff is really highly correlated in this graph. So there's not a big difference in when we use a small cutoff or a high cutoff. But the main difference is that when we have a lot of biases in our data set, a deeper cutoff offers more robust results. So even though we are only showing the top recommendations to the users, it may be more useful in an offline setting to use more recommendations just to discriminate which recommender system is better or not. For sure, afterwards, we have to perform user experiments to really see if these results correlate with the user behavior.
Right. Or just do these kinds of analyses next to your evaluation at top 5 or top 10.
Okay. Yeah.
Okay, thanks.
Okay, let's thank our speaker, Daniel. And